So welcome to the lecture on mathematics of generative modeling, and today I will try to wrap up a little bit of a portion in generative modeling where we do text to image type applications, and it's a simple change to what we have done. So basically we will introduce some conditional. So let us try to see this. So far we have focused on just the data distribution. So this is the data distribution that we have focused on, but we may be interested in learning some conditional distributions. So let us say P of x given y. Okay, so and such conditional will be useful when we want to kind of control the data generation process based on the condition y. So here y is the conditioning information. Okay, so just write down y is the conditioning information. Okay, so and this essentially forms the backbone of text to image type of applications. Okay, so for instance, what we have seen very recently in the news is DALL-E 2 and ImageGen. So this is from OpenAI, which is also behind GPT-3 and 4, and then we have ImageGen, and this is, I believe, from Google. So these are the prominent text to image, but there are also open source ones like Stable Diffusion. So these are essentially applications or demonstration of diffusion based model where we input text and then we generate some conditional image based on the text. So what we want is how can we train our model or do the sampling for our model with some additional condition y. So a natural way to condition is that we put it alongside the distributions we have. So a natural way to add conditional information is alongside time step information. So meaning, if we write this down, then this what we are thinking of is x0 to t, the joint distribution, and this is something we recall from our the way we started deriving the diffusion models. So this is p theta xt minus 1 xt and t equals 1 to t. So here this is the first step that we wrote in the diffusion model case, and then what we want is that we want to bring in the conditional. So for the conditional we will just add y everywhere basically. So for conditioning we put a y, so this means x0 to t y, and this is probability of xt, and p theta xt minus 1 xt yt, and t equals 1 to capital T. So this is the change that we have compared to what we had before, and compared to what we have now is that this is the y, additional y that we put now. So everywhere we will put the such y to condition the generative task. So what could be what could be the applications of this? So applications, continuing, the applications could be, for instance, what could be y? So that's the general question we are asking. So this could be let's say low resolution to high resolution. So this is called image super resolution. So you are given a low resolution image and you may want to make it high resolution, and this could be extended to videos. So videos are nothing but like many images within certain frame, I mean within certain seconds, like 20 frames or so on. So it can also be used in video super resolution task. And so this Y could be a low resolution image, and what you want to generate is a high resolution variant of that. So that could be one possible condition. And second is the obvious one, is when Y is the text encoding. Okay, so I can say like text could be, let us say, a cat making chapatis. So this is the Y that I may put in my model, and it will focus on producing images that refer to this. So these are some of the applications, like let's say we listed out 2, and then with this additional condition, what are the changes we will have when we are learning the model. So the variational diffusion model, in this case, now the changes we will have is that we will have additional Y. So this is x theta, xt, t, and y. So earlier we had xt, but now we have additional y, and this is what we are trying to approximate. And x naught, that's it. So the image that we have, and then we had epsilon theta, which is xt, t, y, and this we are trying to predict it as epsilon naught. Okay, and so on. So if even we want to do the score based model, so then this is s theta, xt, t, y, and this is the score theta, and yeah, so this is our score for the this is the prediction for the actual score, and this is the prediction score, and this is like approximately equal to that. So what we see here is that this y could be added in our model as an additional step when we want to do conditional generation, okay, based on whatever condition we have. As I said, this y could be any condition that you wish, okay, and then you will train on that, and then it will learn how to produce based on those conditions. Okay, even people are doing multimodal now. Okay, so y could be even audio. Maybe you feed in some audio and say, okay, based on the audio you generate something. Okay, so extensions are many. So let's see now if we do this, right? So this is the abstract level, like so we will put y, and then this is what we may have. But let us see what are the problems we will face if we put condition on y. So one of the problems could be is that your condition might make the model lose diversity. Okay, so because you are conditioning, so it may get very focused on the conditions that you have, and it may not diversify. Okay, so this could be the one of the issues, so that we need to kind of look into. So in this class, then we have a guidance based approach, and so we have like we will build it as a classifier basically. So I will be very precise now. So then so we will, so kind of the way it is that when you will train the model, then somehow the model should learn based on the, so y could be your class. Okay, so whatever x is being generated, whether it refers to that class or not. Okay, so then it becomes a internally there will be a classification term there. So now we will look into that detail. Okay, what I said. So but then later there will be an improvement where we may want to get rid of the classifier, because learning classifier from noisy images, we don't have pre-trained classifiers that can do such job very well. So we will arrive at classifier free approach. So let us see if it doesn't make sense now. Let us see what I said. So then we have classifier guidance. So if we train our model like that, where with a condition, then it may happen that, so the issue that we have, it's good to put in the notes, that models trained by conditioning may learn to ignore or downplay any conditioning information. So although I'm putting a condition there, but if it's not done well, what is the guarantee that the model will even give importance to the conditions that you are giving? So hence, that's why we will go into the classifier idea. So this is, and so this is one, and the second one is if we do, so if we do put this condition, then diversity could be at the cost of diversity. Okay, so guidance, which is the classifier guidance that we will describe soon, is proposed as a way to explicitly control the amount of weight the model gives to the conditioning. Okay, so with this view, let us derive basically the classifier guidance. So by Bayes' rule, what we have is grad log p xt given y is grad log of, so we will use the score based approach. So p y given xt divided by py. Okay, so we are looking at the scores, right? It's a condition score now. So earlier score was grad log p. Now we have the condition with y, and we use the Bayes rule to write for this p xt given y is py given xt, p xt divided by py, and then because of the log it will split. So this will be grad log p xt plus grad log say p y given xt minus grad log py. Okay, this just I have expanded, and taking grad is a linear operator, so it applies on everything. And then, so the last grad will go to 0 because these are all grad with data points, right? In the score, we always take grad with respect to the data points. So I have removed this grad, but it's evident. So this goes to 0 because it's independent of xt. Okay, so what we are left with is these. This is the unconditional score, and this is the conditional score. Okay, or I mean not conditional score, but it is essentially a classifier now. So given an xt, whether it belongs to the class defined by y. Okay, so and this is the unconditional score. In fact, this is the score that we are familiar with. This is the additional term that came because we are looking at the conditional output, conditional generation. So this is unconditional score as before, and this is the additional term, and this is the adversarial, we call it adversarial gradient. Okay, so so this is the derivation we have, because in our model we will be, if we are doing score based approach, then I have removed this, right? So f theta xt, this will be trying to predict that, right? So in the score based approach, this is what we are trying to match. Okay, so in the score matching, earlier we were trying to match grad log p xt, but in the conditional case now we are matching these two. Okay, so so the first term is learned as before, and then additionally we have now the classifier. Okay, so this classifier is a little bit troublesome because this classifier has to know, given a class level, it has to learn from xt, which is a noisy image at the tth time step. It has to learn to predict from an arbitrary noisy image the assigned class. Okay, so this seems to be a very difficult task, because no matter how much you train, you may train a lot from very, very noisy images. You build a classifier that tries to learn, given this noisy image, I can predict this or not. But that is a bit not so easy, right, to pre-train a classifier like that. Okay, so later we will do an improvement on this where we will get rid of that. Okay, so but for the moment, this is the So here, so the model will learn these two quantities, right? So let me write that in the notes. Okay, so in classifier guidance, hence in classifier guidance approach, what we have is that score of unconditional model, a diffusion model. So in this case, okay, so we are writing the same things in words now. So log p xt is learned, okay, is learned, and alongside classifier is learned. Alongside classifier is learned. I mean, classifier is learned, or what is the role of a classifier? I can state that. So classifier, what it does, it's supposed to do is that takes alongside the classifier, that takes arbitrary noisy image xt and it's supposed to predict and attempts to predict condition y, okay, and this will be, this is the problematic part in the classifier guidance. And let us assume that even with this model, let us say we have some classifier that does some job, and we have this, and in fact the initial paper was published on this only, where they had this exact model, and so this corresponds to references 10 and 20. So it's good to write these references, the papers that introduce these. So 10 in the notes, okay, or because we mix and match notes, so let us create our set of references separately. I will put the whatever notes I'm using, but in our notes let us keep it in our way. So here it's 10, so let us say, in our case this reference is Yang Song et al. Okay, there are other authors, but you just write et al. And so this is score-based generative modeling through stochastic differential equation. So we have also seen this before, score-based stochastic differential equation. So as we have seen before in the energy-based model, the xt could be seen, the forward process could be seen as a continuous dynamic, and we had this diffusion equation written in a stochastic ODE form. I have done all this, and then from there, if we discretize via some Euler scheme, then we can get this xt in each time step, and this is where they also introduce this conditional approach, okay. And then so you have this reference, and there is one more, and 20, okay. So we have this reference B, and this is diffusion models. So let us first write the authors. Profula, Fulla, and Daribal et al. And this is diffusion models beat GAN, diffusion models beat GAN on image synthesis, and this was 2021, right. So, and these are, for the moment, these are the two references where these classifier guidance and were used. So now, so one of the things is that we may put some weightage here, okay. So it may be that, so here you can see that if this term dominates, then the diversity will be lesser, because now the model will focus on images specific to the classifier, okay. And then if if this term is completely neglected, then you are focusing completely on the diversity. So what they did is that they put some weights between this to control whether I want more diversity or whether I want more images specific to the conditions. So then there will be less diversity. So you can put a weight there in these two terms, and you may control a trade-off between diversity and images corresponding very closely to the conditions that you have. So hence a small modifications that were done was to introduce fine grained control. To introduce the fine grained control over sample diversity or the conditions. So what we have is that we put a weight there. So grad log pxty is grad log pxt plus gamma, and then grad log of p of y given xt. So this is the additional weight that we are talking about. This weight is introduced, and now because at the end of the day all this goes into optimization, and if I have higher gamma here, then it will focus on the classifier more, meaning more importance is giving to the conditions. And so depending on this, this may be like a hyperparameter now. When you are implementing this, there may not be a sure shot way of what gamma is. You have to play around for a given application and produce this. Okay, so the two cases here are obviously like if gamma is 0, then it's a pure diversity, and if gamma is high, then you're more on the conditions. So I have already said this. So, but the problem remains, what I said in the beginning, is that you still are dealing with a classifier. So can you get rid of classifier? Okay, so that was the next update on this. So drawback of classifier guidance. So drawback of classifier guidance is that it relies on this classifier that's run separately. Like we know this, but then this classifier is a classification problem. Okay, and we need a classifier that learns how to predict y from a noisy image xt. Okay, so this will be an additional task here. So this requires separately learned classifier, and the problem is that classifier must handle arbitrary noisy inputs. Classifier must handle arbitrary noisy inputs. And which most pre-trained classifier don't know, right? So which most pre-trained classifiers are not optimized to do. Right, so this is a not so easy problem, right? Because in general, when we build a classifier, then I have like let's say image of a cat or human or so on, and then it has to predict it's a human or not. Okay, so this kind of classifiers we're thinking of, but now the problem is that it may be noisy also, right? So it's like this, and then it has to predict how much percentage it looks like a, because classifier prediction could be also like in terms of percentage. Let's say between 0 and 1 it may say, okay, let's say it's like 90% human or so on or something like that. Okay, but based on that it might say, okay, let us say it matches closely with the class that I'm looking for. So in general you can see that predicting from noisy image a class is a difficult task. Okay, so then there was a need to kind of get rid of building such classifier. Then the next approach was classifier free guidance. Okay, so here we want to get rid of the classifier, and it's a very simple idea. So basically it will use the equation this one, and because you have two equations. One was without the gamma and one is with the gamma. So two equations, and then you eliminate this classifier with the help of two equations. So it's a very simple idea. So then we go to classifier free guidance. So then we move to classifier free guidance. So in classifier free guidance, this is the reference 21. So let us say this is our reference C. So this is Jonathan Ho et al. And this is, well, the title is classifier free guidance, and this appeared in 2021. In fact, this appeared in workshop, NeurIPS workshop. Okay, so this is the paper that introduced this classifier free guidance, and as I said, the idea is very simple. From the first equation that we had, we solve for the classifier. So first equation without the weight gamma. So we have grad log p y xt is grad log p xt given y minus grad log p xt. Remember that these grads are always with xt. Sometimes I forget. So this is just the first equation. So basically, earlier we wrote this is equal to this plus this. But now we solve for the classifier. And then the second equation was with the weight. And in the second equation we had, with the gamma, right? And so basically I'm thinking I just put the gamma here, and then we will solve for this is right, gamma was here, and I'm supposed to get rid of that, right? So okay, that's fine. So let us start with this this equation, and basically the second equation. And in second equation we replace the classifier. So what was the second equation? Second equation was with the gamma. So grad xt log of p xt given y was grad xt log of p xt plus a gamma of grad xt log of p xt. So basically here we are going to replace. Okay, so here this guy is going to be substituting this guy, and if we do that, then we get rid of the classifier. Okay, that's the idea. So we have grad log grad xt log p xt given y, and this becomes we take the gamma common, grad xt log of p xt given y, and then plus 1 minus gamma grad xt log of p xt. So we have got rid of the y given xt. Okay, that was the whole plan. We got rid of y given xt. Basically the classifier is gone, and we will try to learn this, in fact. Okay, so we have, what we have is a conditional score. And this is our unconditional score. So basically we have to learn, given a y, what could be our for a given y, what are the noisy images that I'm going to produce in the forward pass. Okay, and we have the second term, which is the usual one, with just probability of xt here. Okay, so once again, gamma is a term that controls our learned conditional model. So obviously when gamma is 1, then the model, so when gamma is 1, the model explicitly learns the model learns the vanilla conditional distribution, the vanilla conditional distribution, and then when gamma is greater than 1, obviously it will prioritize. So basically gamma greater than 1 means in fact okay, it's going away in fact from the log pxt term. Okay, so it's more and more into the conditional. So when gamma greater than 1, so let us write this fact, when gamma greater than 1, the diffusion model not only gives importance, so prioritizes the conditional score not only prioritizes the conditional score function, but also moves in the direction away from away from the unconditional score function. So basically we have this interpretation of these gradients when we were discussing the score matching and so on. So gradients give you some vector fields, right? So in this case, if I'm basically, if gamma is greater than 1, then this is negative. So it means like my vector fields are even going in the opposite direction of the data distribution. Okay, so it's more in the in this. It would be interesting to kind of plot these things and see these things in actual practice, how this gradient fields change and so on. So so this is all about the conditional generations and classifier guidance, and then we extend this to classifier free guidance, and this is what exactly is the technology used in DALI 2, ImageN and so on. You give a prompt in terms of text and it generates images for you. You can look for some codes. The ideas are already now in detail here. You can just look into the code and you will feel it very nice going through the codes now, given that you have a proper understanding. So now what we will do is that we will move to another set of generative models which are based on, basically they are based on sequence to sequence models. So all the new variants, I mean the new, like let's say the apps, okay, the technology may not be new, but the apps that you have in, let's say, like ChatGPT that's there, so they are based on these sequence models. Okay, so next word predictions, next token predictions, and these are quite powerful. So next 4 lectures, including today, we will get into this, but we will start with something basic, which is sequence models. So in the sequence model framework, what I am planning is there are two broad categories that we will plan for. So our aim is to get into let us say 2 types of, they are related also, but broadly we will get into 2 types. So the one of them is autoregressive. In autoregressive models, just some highlights. So these are class of generative models that model the probability distribution of a sequence by decomposing it into product of conditional probabilities. So we will see explicit representation in detail. And so these are the type of models that model the probability distribution of a sequence by decomposing into product of conditional probability. Okay, so if it doesn't make sense, we will see some examples as well what this means. And second, in auto-regressive models, each element of the sequence is modeled as in auto-regressive models. Each element of the sequence is modeled as a function of the previous elements which act as a conditional variable, which act as conditional variables. Okay, so right now we are just writing things in words just to see what are these, and obviously we have to make these things concrete. So as a generative task, as you can see, we can use this for generations. Okay, we are learning conditional probability of what I have seen before to predict xt given what I have learned until xt. So if I know this distribution, then having seen xt, I can predict xt plus 1 because I have the distribution for that. So this is how the modeling works, I mean the generation happens. So this is B and then this is C, is autoregressive models can be used to generate new samples by iteratively sampling from the conditional distributions. From the conditional distributions until the entire sequence is generated. So this is the background for autoregressive models. We'll make it precise, and the another class of problems that we will study is with here. So this is something called a normalizing flow. They are related. Okay, they are related. There is a fundamental difference between the two. That's what we will study. Within the class of autoregressive models, you may have cases like RNNs, okay, LSTMs, transformers. They would belong to this autoregressive class. Okay, so that's why sometimes you will see people talk about ChatGPT is an autoregressive model. Okay, so our goal is to understand things from fundamental point of view, and the special cases RNN, LSTM belong to this class. So that's my aim. Okay, to understand from the foundation, not just the special cases. I will cover LSTM, RNN, transformers, everything, but going from the basics. So as I said, in this 4 lectures, my goal is to cover these 2. So within this we have normalizing flow. So the another topic is so in normalizing flow, just like few points. Okay, these are a class of generative models that transform a simple base distribution into a more complex distribution by a series of invertible transforms. Okay, so there will be a similarity between autoregressive model and normalizing flow also, because autoregressive model is kind of trying to learn the conditional distributions. Having seen x1 is trying to know what could be the PDF of x2 given x1. Having seen x1 and x2 is trying to predict what could be the probability distribution x3 given x2 and x1. Okay, so these are the things autoregressive flow models do. And in normalizing flows, we are saying, given a base distribution, okay, let me go up to certain distributions by a series of transformations for the PDF. Okay, so initial base distribution I have, let's say standard normal. Can I generate something complicated by doing some transformation of these random variables? Okay, so we have seen few things like that. So for instance, in probability statistics, someone tells you this and then find the probability density of this. So basically from here to here, you have transformed via function this. Okay, but I can keep doing that, right? So basically from the base distribution x follows certain distribution, and I will apply some function, and I will apply some another function, and then I may create something complex depending on what f is. But then in normalizing flows, a requirement is that these f are need to be invertible. Okay, so we will see why the invertible is needed, because in fact if you recall the formula for the transformations, you needed invertibility, right? So that's exactly the point. Okay, PDF of a transform distribution, you have to compute the Jacobian of the inverse and so on. So that's why the invertibility is needed. Okay, so for the moment, the normalizing flows are like that. Autoregressive flows are like learning conditional distributions. Okay, so these are the small differences. Let's see a few more. So these transformations can be combined to form a flow. Okay, so basically we can combine these. So these transformations can be combined to form a flow model that can be used for density estimation or generative modeling or so on, right? Or generative modeling. So this is what we will see, how this will be used in our case, how it will be used in the generative modeling. And same thing for the autoregressive, we will see how it will be used for the generative modeling. And the main challenge in the normalizing flow is to define these transformations, obviously. And the inverse is the tricky, right? So that's why you will see people kind of look for transformations that are easier to work with. So you may not have the perfect transformation, but something that's computable. So we will see those things later on. So the third point is, so normalizing flow have gained popularity due to flexibility and ability to model complex high dimensional distributions. Okay, and so that's the selling point of normalizing flow. And obviously you will see that in almost all this, whether it's autoregressive or whether it's normalizing flow, at some point neural network is used, and that's how these models become very powerful. And we will see those specific cases. So a popular approach or the main challenge in normalizing flow is to design transformations that are computationally efficient and can be easily inverted. Okay, so this is indeed the main challenge that I also remarked before. I'm doing series of transformations, so are they easy to work with? Because at some point I also need invertibility. Okay, so So that's where by doing this various approximations you get a lot of papers. Okay, you can say that I want to do this kind of transformation, that kind of transformation. It's easier. The computational complexity is lower. So many kind of papers come just with this design of different transformations, and it could be very specific to certain task. Okay, so same thing may not work for every task. So different transformations may be needed. Okay, so some of the popular ones, and as you can guess, whenever we talk about something related to transformation and so on, naturally neural network comes in picture. So if I have some supervised data, I can use parametric models like neural network, and maybe those transformations will be learned automatically for me. Okay, I may not have to think about optimal transformations. So a popular approach is using neural networks. So popular approach is you construct transforms using neural network. And obviously, as I said, in this case, we are expecting that the data is there because neural networks are parametric model and they need data, right? So learn from data. So some of the popular normalizing flow architectures, or you can say methods, that were proposed, we will see them in detail, but let us first note them. So some popular architectures of normalizing flow include real NVP, GLOW, and MAF. Okay, the full form and all this will be discussed later on. These are some of these are quite new. Okay, so some like maybe 5-6 years ago. So applications of normalizing flow are in image generation, obviously, density estimation. These are the applications, and what I will do is that I will also write some points showing the differences between auto-normalizing flow and autoregressive flow and normalizing flow. Okay, these will be standard questions asked in the exams as well, like tell some differences, things like that. So it's good to kind of have a clear understanding of what are these models and how they differ. So hence I have made a couple of points about differences. So key differences between autoregressive and normalizing flows. So let us point out few differences. So autoregressive flows model the joint distribution using model joint distribution using chain of conditional distributions, using chain of conditional distribution. Whereas normalizing flows model probability distribution by applying a series of invertible transform transforms. Autoregressive flows are computationally efficient. But may suffer from slow convergence. suffer from slow convergence. Let us use it here. So, but may suffer from slow convergence and are limited to modeling low dimensional data. On the other hand, normalizing flows, so here, on the other hand, normalizing flows are flexible in modeling high dimensional data. But can be computationally expensive, but can be computationally expensive due to the need to evaluate the Jacobian, evaluate the determinant of the Jacobian in each transformation. Okay, so and the last point is in autoregressive flows, the conditional distributions are typically modeled as Gaussian or discrete distributions. Whereas in normalizing flow, the transformations can be any invertible functions. Okay, so in autoregressive flow, we usually stick to Gaussians or discrete distributions, but here you have a bit of flexibility in using any transform basically you want. Okay, it should be invertible and obviously easy to compute and so on. Okay, so I just thought that it's good to kind of put this because sometimes people don't have a clarity on the differences. Okay, then we go to so we will start with autoregressive flows. We'll build the background and then we will derive the specific cases or the examples that I have listed here. So let us start with the sequence models. Okay, sequence models are kind of the best problems that fit in the autoregressive model. So suppose we have x in R d by d, okay, where x is kind of, you can think of this as matrix now. So you have d-dimensional vectors stacked t times. Okay, there are t d-dimensional vectors, so that's how we can see x bar. So which is a sequence of, so where maybe I can write, since this is the first time, maybe I can define this what I really mean. So this is like x1, x2, xt. So these are like the concatenation of these x at times step 1, x times step 2, and we combine them, we get x bar. Okay, so these are the sequence we are talking about. X1 is the first in the sequence, x2 is the second in the sequence, xt is the last in the sequence, and each of these is a d-dimensional vector, okay, where xi's are d-dimensional vectors. This is a sequence, okay, that's how we define sequence of d-dimensional vectors. So I think the way notation is used is below, actually, subscript. So let us use that. It's d here. So this is a sequence of d-dimensional vectors indexed by d-dimensional vectors xt indexed by a discrete temporal. So basically here the t lies between 0 and less than t. So our goal is to learn a joint probability distribution. I mean, after having observed, not joint, let's say this is a conditional. So after having observed x1 to xt sequence, what could be, or let us say xn sequence, what could be the prediction for the next. So we are interested in modeling the unknown distribution P over a collection of sequences xn taken from P, okay, from distribution P. If I have seen x1 to xn, okay, so here x1 to xn in our notations is this whole set of these sequences. Okay, so x1 itself, x1 bar itself is a sequence up to t. Okay, let's say, and x2 bar is another sequence, and so on. So we have these samples of sequences. So obviously we use subscript to denote one of the entries in the sequence. So x bar 1 subscript 1 will be first, x bar 1 subscript 2 will be second, and so on. Okay. So this is the problem we have, where you are given a sequence of data. Here we have sequence of data one after the other, and you are supposed to learn a probability distribution based on that, so that you may do a prediction for the next in the sequence. Okay. So how do we model such problem, right? So one possibility is that I collect all. I don't take into account the ordering of the sequence. Since this is a sequence, there is ordering, but I may not consider them as a sequence. Okay. In that case, I may kind of consider the whole data of length t times d. Okay. So that's one possibility. So let us see what are the issues if I disregard the sequence and the ordering of the sequence. By disregarding the sequence, I am saying I just stack them as one. So one way to approach is to ignore the temporal structure. Ignore the temporal structure and simply treat sequences as vectors in RTD. Okay, so as you can see, I have the t times d in place of t times d. I am just taking this as RTD. Basically, I make a one big vector, okay, of all this, and treat them as just one big vector of dimension t times d. So that's one possibility. Okay, I just make it one big vector. So this is obviously we can do that, but there are reasons why we want to incorporate. So can do this, but there are reasons why we might want to incorporate temporal structure in our models. Okay, so what we're saying is that giving importance to temporal structure is important in for these reasons. So the length of the sequences can be a variable. So that's one problem, because each time we are looking into the sequences, each may have different length. Okay, so that may create issues in having this variable length when we do the stacking. Okay, so then the second one is the collapsed vector can be very high dimensional. Okay, so if I have a sequence of a million then the stacked vector is that big, processing them at once will be very tricky. Whereas in sequence I may take one word at a time, one token at a time, one character at a time, one sentence at a time. Okay, but stacking them requires processing of these one big sequence at once. Okay, so that's another possibility from computational point of view. So collapsed vectors in RTD can be very high dimensional. So basically it's very high dimensional, hence that's also another reason why we may prefer having sequence approach. Okay, from memory point of view and all, it can help. So what we're saying is that we have a sequence problem, x1, x2, x3 and so on. This is how we see texts when we read in books and so on. These are sequence of words and so on, and there could be other time series problems. Okay, so where temporal dependencies matter, what came before determines what could be predicted next. So we could take this as a raw, disregard the temporal structure, stack them as one big vector, but then there are these two reasons that I stated. It may not be very feasible to do that, hence there is a requirement to have build sequence model separately. So these concerns 1 and 2 are tackled via so-called autoregressive models. These problems are tackled via autoregressive models. So what is autoregressive model? So we can slowly build the maths part of this. So given a collection of learned conditional distributions p hat xt given x less than t. So given a collection of learned conditional distributions, basically these are the conditionals that we have learned. We use p hat for the learned one. So basically for every sequences less than t, x1, x2 up to xt minus 1, we have learned what to predict as xt. Okay, so then having learned this, we can predict xt, right? We can sample xt. So we can sample from model by iteratively sampling okay, that's so I have learned a distribution, so hence now I can sample having seen t up to t minus 1. I know how to predict xt. So the point is that I can do this iteratively, right? So that's why this word iteratively is now interesting, because having seen a input of length t, my model now learns how to predict the t plus 1 entry. But then having produced xt, then my model can iteratively predict what is xt plus 1 as well, okay, because I will just skip the first the very first one, right, let us say, okay. If so this means that I can keep producing xt, then I may produce xt plus 1, xt plus 2, and so on. So this way we can iteratively keep sampling. So that's already a way we see is how generations can happen, okay. So obviously we have to know how to learn these conditional distributions. So that's the main thing, because having dependencies on many of the previous ones can be quite difficult to kind of estimate such distributions where you have dependencies up to previous ones, all previous ones, okay. So these are the things we will see. So this is the plan. This is exactly what autoregressive models are supposed to do, okay. This 3 lines is what is the model for autoregressive. Now the only thing will be how we are going to build on this. So whether we will have a simple regressive model where we have a more let us say of p let us say it looks into the p windows of the all previous xt, so how big you want, right. And then there is a linear, there is a neural network based model, and so on. So that's where we will build, but then this is the main aim for us, okay. So hence we will start with something very simple, let's say linear. So linear, and let us say first order. So first order means that if you have seen some recursive equations, the first order would be like it just depends on one of the previous iterates, okay. So that's first order. If I look into the recursive equations of second order, then it depends on t minus 1, t minus 2, and so on. So this is the idea here, is that it will be a kind of recursive equations to get t from something previous one, right. Now how many previous ones is something we have to think. So we can start with very simple one where xt depends on xt minus 1. So that will be the linear autoregressive model, okay, and more specifically it will be called AR1, okay. So let us see what is that AR1, autoregressive of order 1, okay. So linear autoregressive models So we define that. So for a simple sequential data, for a simple example, let's say of a sequential data, let epsilon t comes from normal distribution with 0 mean and variance sigma square, and these are IID. Then consider a scalar sequence of observations, let us say x t by 1. So we call it scalar because this d is 1 in our case now, okay. And let us say this is defined by, so we are starting from something simple, okay. So defined by the linear dynamics So let us say this is xt is rho xt minus 1 minus mu plus epsilon t, and x1 the first one is defined to be mu plus epsilon naught. So as you can see, this is a sequence generating recursion where x1 is given to you, and epsilon naught that you see here is you are sampling from normal with 0 mean and variance you fix to be sigma square, okay. So you can generate x1. To generate x1 you have some number mu, and then epsilon naught you can sample, and then you generate x1, and once you have x1 you put it here and you sample epsilon 1 now, and hence you generate x2 and x3 and so on. So that's a way to generate sequences. So this is a very simple linear autoregressive model, but it will give us some clarity on how to go about sequence models, what are the difficulties we face, and how neural networks later on will be useful in doing learning more complicated recursions than this very simple one, okay. So this is called autoregressive AR1, okay. So as you can see, we can have ARP also, okay. So these dynamics are referred to as, so these dynamics are referred to as autoregressive process of order 1 or AR1. So there is a book by one can refer this book. This is called this is by Rao, 2020, A Course in Time Series Analysis. So here in this books you can kind of see more details about the variants of autoregressive models. So this is AR1, then we can think of ARP in general. So in the P I will have P of the previous terms basically. Okay. In AR1 we have xt depending only on one previous term, which is xt minus 1. Okay. So these are autoregressive AR1. So here order 1 refers to the fact that xt is a function of only one previous observation, which is xt minus 1. So we are familiar with such models where the current depends only on the previous one. That's exactly what we have used in variation diffusion models, where we assume the Markov property. So this is nothing but a Markov property. So this in this case also known as Markov property. So now if I want to compute the probability distribution of xt given xt minus 1, okay, and then I am so to do that I want to know what could be the mean and the variance, because at the end of the day these are some scaling or translations of the normal distribution. So we expect that the scaling and transformations of a given normal distribution will remain normal. That's what we're expecting, right? So this will be normal, but then we are looking at what would be the mean and the variance. So basically what I need to compute is the mean. So what is the mean of xt? So we will do expectation of xt and see what do we get. Okay. So clearly probability of xt given x less than t is a normal distribution. Okay. So it's a normal distribution for sure, but then within in this, to define a normal distribution I need mean and the variance. So then I will go ahead and compute mean and variance given the xt is like this. So to compute mean we have that we compute the expectation of xt. We compute the expectation of xt, then expectation is linear, so rho comes out, and this is expectation of xt minus 1 and minus rho mu plus mu plus expectation of epsilon t 0, because that's sampled from normal with 0 mean. So what do we have? What do we have is that rho of xt minus 1 minus mu, that's right, and then plus mu also outside, right? Yeah, and important thing to note is that xt minus 1 is given. Okay, because with this condition we know xt minus 1 is given, so expectation of xt minus 1 will remain xt minus 1, because xt minus 1 is given, right? So it's no longer a random variable, right? So with that the mean is rho, and basically I can just keep the rho common itself. So xt minus 1 minus mu, and this goes to 0 since epsilon t was sampled from normal 0. So the mean of the epsilon t is 0 for sure. So and then this is plus mu. So this is our expectation of xt. Okay, and we need variance also, and to compute the variance, so to compute the variance again we do the variance of xt. So if we do the variance of xt, yeah, it seems it will be I believe it will be just sigma squared, right? So let us compute the variance of xt. So variance of xt will be variance of, put the expression for xt. So this is rho xt minus 1 minus mu plus epsilon t, right? So variance, these constant terms go away, right? Because variance of a plus x is variance of x. That's what we recall from probability. And then we also recall that the variance of ax is a squared variance of x. So this also we recall from probability. So these are the two things we will need to simplify this. So this is like our a, or even these guys all are like a, rho mu mu and sigma t, they are all like a. So in the variance they will not contribute. So this will be essentially variance of rho xt minus 1, which from the second formula rho square will come out. So this is variance of xt minus 1. Oh, I made a mistake. So actually these guys are all, what is not constant is what is random variable is epsilon t, but everything else is constant because t minus 1 is given, right? So what we have is that all these guys are constant. So let me write this here. So these guys are kind of constant, not random variable, right? So variance of these will be 0. So this will be variance of, because xt minus 1 is given, so now it becomes it's no longer a random variable now. So this is epsilon t, and we know that epsilon t is sampled from normal 0 with variance sigma squared. So the variance of epsilon t is sigma squared. Okay, so that's our so we have computed the mean and we have computed the variance. So now we can write down the conditional distribution of probability of pxt given it has seen all up to t minus 1, and that's a normal distribution. So now we know the mean and the variance. So now I can write this as probability of this. Hence probability of xt given x seen up to t minus t. In fact, in our case we are looking at just t minus 1. Okay, just in this notation we are writing like this. So this is normal distribution with mean that we have computed rho xt minus 1 minus mu plus mu, and then the sigma squared is the variance. Okay, so yeah, so another interesting thing to note is that by induction what will happen is that actually expectation of xt will become simply mu. Okay, because if I substitute, if I do if I write xt minus 1 again in terms of xt minus 2 and so on, then these will cancel out eventually. Okay, and then we will get to, I mean, if you want you can start from t1, let's say. So what is expectation of t1? So xt1, so expectation of xt1 is rho x0, right? Or our starting point was x1, yeah, x1 let's say. So then we what is expectation of x2? Expectation of x2 is rho x2 minus 1, so x1. Okay, so minus mu plus mu, right? So to compute expectation of x2, I have to compute so basically the rho mu gets cancelled. The best way to see is this one. X2 is rho expectation of x1, but expectation of x1 is mu. So this becomes rho mu minus rho mu, that gets cancelled, and you get only mu. And then you can do this recursively. X3, since expectation of xt minus 2 was mu, it remains mu. So due to induction, the expectation of xt actually remains mu. Okay, so that's a good thing to point out. So note, by induction, expectation of xt is mu, and this is because expectation of xt is rho expectation of x1 minus rho mu plus mu so let us say this is 2, we are starting from 2 So continuing this way, we can by induction we claim that expectation of xt is mu. So such type of process where the mean doesn't change is called a stationary process. Okay, so I mean we say that the mean is stationary basically. So because the mean does not change, we say that mean is stationary. Okay, so we define something called a stationary pth moment. So if you think of mean, then this is the zeroth moment, and we can define this to be stationary for the pth moment. So a time series x has stationary pth moment if expectation of xp is constant for all t, for all time basically. So that's we have just extended this definition of stationary to the pth moment. So in the autoregressive process, in the autoregressive model, we have multiple things here. We have sigma, we have rho, which is the regression parameter, and we have the variance sigma, and so one of the things as a first step we can focus on is how am I going to estimate the mean, let's say. Okay, so suppose, or let us say to simplify a lot, okay. Yeah, so if you want to go, you may go. I will take a little bit. Yeah, I have. Yeah, okay. I will take a little bit longer. Okay, so to simplify a lot, what we want is like, suppose we know rho and sigma squared. Let us say we know rho and sigma squared, and we want to construct the estimator of the density, let's say p hat. So we to construct an estimator p hat given a sequence of length, given a sequence of observations x of length t. So all we need in this is that only thing unknown is mu for the moment, given that rho and sigma is known. So we need an estimator for the mean. So length 3. So all we need is an estimate of the mean mu. Okay, so let us say the estimator of the mean is mu hat. So from the statistical estimation that we have done in the previous few classes, we know that one of the estimates is when we take mu to be average of the samples basically. Okay, so basically what we are thinking is sample mean, will it estimate this this true mean? Okay, so as we'll see, this it won't be the case here because though that was for an IID. Okay, so So what we know is that maybe we can build an estimator based on the sample mean, right? So try the estimator mu hat, which is 1 by t, and sum over xt, t equals 1 to t. So this is what we know. This is the sample mean that we have seen before. And this is known to be an unbiased estimator, known to be an unbiased estimator if this if is like the okay, if the samples are, if the observations in our case the observations are like xt are IID, independent and identically distributed, then we had this result that the sample mean estimates the true mean. But unfortunately, XTs are not IID in our case. Okay, so we have to do some work here. We may not be able to use the law of large numbers. Okay, but in our case, XTs are not IID. Okay, let us say then. So since XTs in our case, if we assume are not IID, then law of large numbers does not ensure consistency of our estimator mu hat. It may not be a consistent estimator. So what do? We will go back to the proof of the weak law of large numbers, and we will see what we can tweak there to make it to get some estimator, okay, which may not be the sample mean, but which may be something else. So let us look into, so examine the proof of law of large numbers, and from there we will get the hint. So in the law of large numbers, we make use of Cheryshev inequality. So that tells us so in Cheryshev inequality we have we made use of this Cheryshev inequality, if you recall, if we did in the last class as well, and from there so in our case, if it was IID, then the variance term would kind of get simplified, but in our case, because the variance will be the same, right, for all the samples, so in this case it's not the case. So hence without the assumptions of IID, we have to look into what this variance term look like. So we will have in this case, so we have in our case variance of mu hat is, so mu we have written it here, this is our mu, and we will apply the variance on this. So if we apply variance on this, then so variance of AX is A square variance of X, so that's, so then we have 1 by t square outside, so 1 by t squared, and then variance of X plus Y, so we recall variance of X plus Y is variance of X plus variance of Y, and then plus 2 times covariance of XY. So this is the formula we recall from the probability part, and it's just that here we have sum of x1 x2 up to t, okay, but this pairwise covariances will show up. So the first term will be sum of the variances of xi, so this is variance of xt and t equals 1 to capital T, and then plus 2 times covariance of xs xt and 1 less than equal to s less than t and less than equal to t, and this is the variance term in our case, because it's not IID if it was independent, xs and xt covariance would have been 0. So we would have got rid of the second term, and from the first term we had variance of xt, and each of the variants were same, so it would have been sigma square and then divided by t square and so on. And from law of large numbers we would have said that if t is large enough, if the sum is large enough, we are taking more and more sample and averaging, then it is a true estimator, because this probability is there is a convergence guarantee that mu hat is very close to mu. So but in our case, yeah, we have this. There may not be IID. So now in this case, we cannot say that the variance of mu hat will go to 0 as t tends to infinity. So if it was IID, then clearly if we look at the variance of mu hat, then it would have been 1 by t square, and then we had t of sigma square, let us say, and plus 2 times 0, and this is sigma by t, and this goes to 0 as t tends to infinity. So this was the case when it was IID, but then this is not the case here. So hence we will look into something that's in a slightly more general case than the IID case. IID case was like the very nice case where the estimator indeed is close to the true, is the unbiased estimator. But so we are looking at the cases where we have some estimate, let's say. Okay. So then we are led into a topic called wide sense testnity. So a time series X is called wide sense testnity if it has stationary mean and covariances are given by So this is a unique property that we are asking for. We are saying that covariance of xt minus k matches the covariance of xs minus k. Okay. So if these properties are satisfied, we say that it's a wide sense testnity. So basically the dependence, what determines this equality is the k, because indexing you can choose t to be something different, s to be something different. Okay. But then so we call that this is stationary in a wide sense, right? So so we may not have IID, but then we are having this as a slight generalization of that, and then we can define a covariance function. So we define a covariance function which is gamma that goes from n to r. So n is the natural number here, and then we define these covariance function as covariance of x k plus 1 and x1. Okay, so that's how we define a covariance function. So with this definition of wide sense testnity, we want to know whether we will have any interesting bound if we are looking at the variance estimate, let's say. Okay, so do we have anything with this these assumptions? So if we look into the variance calculations, assuming that xt's are wide sense stationary, then so in this case what we get is variance of mu hat is 1 by t squared t gamma 0 plus 2 t minus k and gamma k, and k equal 1 to t. And so what we are saying is that this is what we get. okay, as a variance of mu hat. Okay, so the derivations of this we can do this very quickly here. If we look into the second term, which is covariance of xs and xt, okay, that's the covariance of xs and xt. So what are the let us say we look into the into these terms, because there is ordering of s and t. So we can say that we have terms like this. So we have some of the terms like this where we have s and t differ by just 1. Okay, so s and t differ by just 1, in meaning t minus s, this is like the cases t minus s is 1. So in these cases, what are the simplifications we are going to do? So in this case, we see that, so these are all related to, so basically these are all autocovariance 1. So if you recall, the autocovariance also I will write it here. So gamma k is covariance of x k plus 1 xk. Okay, so this is the autocovariance term as well. So what you're saying, we would like to write this in terms of gamma k. So if we look into this, then gamma k is basically and this is last one is 1 basically. So we want to see how this could be written. So so if so this covariance, I can also write this as 2 1. Okay, so it's the same thing, right? So this is 2 1. 2 1 will be so basically we are going from 1 to this, right? So if it is 2 1, then this is like gamma 1. Okay, so this is like gamma 1, and this is equal to covariance of, I can write this as x3 x2, and then x3 x2, then what I will do, because it's a wide sense stationary, so if I subtract a 1, we have to, so my claim is that this will be equal to this. Okay, so basically my claim is that this is equal to covariance of x2 x1, and this is because the time I can pick, the k I can pick is the 1, right? So this is, I can write this as covariance of x2, and so this is minus k, right? So I can write this as x3 minus 1, and this must be equal to covariance of x2 minus 1. So this is like xt minus 1 will be same as xs minus 1. Okay, so this shows that x3 x2 is same as x2 x1. So hence this is also gamma 1, and similarly I can show all are gamma 1. So I have so basically 1 to t minus 1 terms, all are gamma 1. So this is t minus 1 of gamma 1. Okay, now similarly I can look into terms like t minus s equals to 2. So in that case, I will have covariance of x1 x3 plus covariance of x2 x4 plus dot 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 plus covariance of xt minus 2 xt, and this I claim will be t minus 2 gamma 2. Okay, in the same way we can say that each of these terms are equal, and this guy is gamma 2 from the, this is nothing but the autocovariance, and then each of these guys are equal, each of these guys are equal. So there are t minus 2 of these. Okay, so we start from 1 2 and we end at t minus 2. So there are t minus 2 terms, and each of them are gamma 2. So this way we can keep doing this, and then we can look at the k, we can look at the case where t minus s is t minus 1. So in that case we are looking at covariance of x1 xt. Okay, so in this case this will be basically this will be 1 times because there are 1 term, and this term is nothing but gamma t minus 1. Okay, so we have figured out the second term, how the second term looks like. So we have computed this second term, and we have said that this indeed is like this, because we have this these terms here. So we have these terms computed here, first term, second term, and so on, and then we have this last term, which is gamma t minus 1. So that all this we can put in the sum, and then we have the first term also. And in the first term, to compute the first term, what we have is what we are looking at is this guy for the first term. So this is like sum of the variance of xt and t equal 1 to t. So in this case, for t equals to 1, this is variance of, this is like a covariance of t equals to 1. So this is covariance of x1 plus covariance of x2 plus dot 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 plus covariance of xt. So this is the sum we are trying to do, and then we have covariance of x1 will be same as covariance of x2 because with the covariance property, I do have that covariance of x1 is if this we can write this as so basically this we can write this as we can use properties like this again. Okay, so here we have we can write this as 2 minus 1 or x1 x3. Okay, so 2 minus 1, and this will be x2 x okay, x1 1 minus 1, x2 2 minus 1, right? Okay, so x2 2 minus 1, that's okay. So with our assumptions, variances are the same for x1 x2 x3, so hence they will be all same in this case. So the variances will be same, and it will fall back. So the variance of x2 will be same as variance of x1 and so on. So hence but the variance of x11 is gamma 0. As you can see, if you put k equals 0, then you have covariance of x1 which is exactly the variance, and these other terms are also same as the variance of x1. Okay, so then we have gamma 0, and there are like t terms, so we have t of gamma 0. So this is what is found here. Okay, so hence we have derived these two expressions here. So now that we have derived it, we can write mu hat is 1 by t squared so this is equal to gamma 0 by t plus, I can take t common. So if I take t common, then I have 2 by t, and this is sum over 1 minus k by t. So k equal 1 to t, and then we have gamma k, and this overall we can drop the negative term, and then we get an upper bound. So then we have gamma 0 by t plus 2 by t and gamma k, and k equal 1 to t. So earlier we said that if we had IID, then the mu hat which was the sample mean is a unbiased estimator of the true mean, meaning that if t tends to infinity, then it does goes to the true mean. But if we so in our case xi may not be IID, so hence we had this generalization where we looked at wide sense stationary sequences, and then in that case we looked at the variance, and then when we look at the variance, then we did some simplifications and so on, and then finally what we see is that for the variance of mu hat, if it has to kind of go to 0, let's say, then ideally what we expect is that this is this decays as well. Okay, so so we must have gamma k tends to 0 as k tends to infinity, and and if it decays, so if it decays very quickly, okay, then the estimator will converge. So in the Chebyshev inequality, on the right hand side we have the variance of mu hat. So if this mu hat goes to 0, and this will go to 0 in this case when gamma k decays, right? So then will converge in probability. So if gamma is summable, so hence we are looking into this now. So if gamma is summable, then let us say, so by summable mean that it sums to something which is finite. So if gamma is summable, that is gamma k equal 1 to infinity is finite, then variance of mu hat will be order of 1 over t, because in that case if this is finite, then this goes to, so basically this is also something finite, we have this finite, then everything now depends on order of 1 over t. Okay, it will decay at the rate of order of 1 over t. Okay, which seems very similar to the order we had also in the IID case. So let us stop for today.